All right, let's get started. Okay, so I've gotten this question a lot. So I'll look at that method and tell me what's wrong with it. What the error, and also what the error message you get is when you do that. Yeah.
Parentheses.
Where's the parentheses error?
Around the strings.
Well, I'm not seeing what you're seeing, but that's not the error I have in mind. Yeah.
There isn't any return statement in the scope of the method, right? Or in the
Well, okay, you're saying there isn't a return method in the scope of the method. Well, sort of. It's yeah. Okay, he said it ends with an else if instead of an else. And that's also sort of right, but it's not the fundamental problem. The error message you get is something like, this method is supposed to return a string, and it doesn't. And students look at it and say, all it does is return strings. What's it talking about? So it's kind of a misleading error message. What's the bottom line?
Is it because there's an integer as the parameter for the string?
No, it's not that there's an integer parameter. Yeah?
Those are all if statements, so it sees that there's a chance that it won't return that.
Okay, so what the compiler does when it's translating your program to something the computer can run is it checks to see, it asks the question, is there a way for the flow of control to reach the end of the method without encountering a return statement? Okay? So is there a way, is there a parameter that could be passed in such that none of those three return statements would be executed? Yeah? You could, well, that's a double, so that wouldn't work. Yeah?
you could assign it a null.
Well, no, n can't be a null either. So here, I actually didn't try this out. I'm just assuming this would cause that compiler error. We can look at it and say, yeah, n's either got to be less than 0, greater than 0, or 0. And so one of those would be returned. I suspect the compiler isn't smart enough to make that deduction. I may be wrong. And it might just say, yeah, it's possible if none of those ifs are true, that we hit the end of the method without having anything returned at all. Okay? And you run into this in PS3 where you write conditionals. So what's a way to convince the compiler that there's no way to escape this without hitting a return statement?
Get rid of that if n equals 0 part.
Right, we just get rid of that, so we have an else at the end. It does the same thing. If the number is not less than 0 and it's not greater than 0, it has to be 0. But just to make it clear that there's three possibilities and there's no way to get there's no way to get out of the if without returning something. Just end it with an else. Yeah?
Could we also initialize some sort of string variable called text and set it as quote and then have each of the if statements assign that text
Yeah.
to something and then return it at the bottom?
So what he's proposing is, what if we did, let's go back. What if we declared a variable here, like string result, and initialize it to the empty string? And then here we say result gets negative. Here we say result gets positive. Here we say result gets 0. And then at the bottom we say return result outside of the if. Yeah, that would work. But it makes the code a little less straightforward. I'd prefer that. So it's not like you have to have a return at the end as long as there's no way to get to the end without hitting a return first. But again, the problem I think is the compiler message. If the compiler error was there's a way you can get to the end without hitting a return statement, I don't think we'd have much trouble with it. But the error doesn't say that. It says you have to return a string. Yeah.
Is there a way that you prefer it to be done on problem sets? Out of the two ways that were mentioned, like this way?
Well, I prefer this way,
Okay.
just because it's less code. Shorter isn't always better, but in this case, I think it is. Yeah.
Could you just get rid of that bottom else and have the function itself work as the else statement? Like if neither if or else activates, then it's not going to do an else, but just runs right to return.
Right, so you say get rid of the else, get rid of these braces, just have return 0 at the end? Yeah. But I don't like that because the three cases are sort of symmetrical in a way, and I like to have just all three cases in the if instead of, you know, the idea would be if it's not less than 0 or not greater than 0, the if ends and you hit the return 0. That would be shorter, but I think this is more pleasing. So, that you know, we're getting into personal opinions at this point, not right and wrong. Did I start the recording, by the way? I suddenly got distracted. Yep, I did. Okay. Any questions or problems about anything before we look at new stuff? Is PS3 coming okay? Hey, let me give you, I'll take your question. Yeah.
In regards to PS3, we were just working on it before. We were having a hard time. We didn't get into the queue fast enough anyway for browsers. Getting from like word to word. It was like doing whole sentences for the big Latin instead of just one word.
So the method that takes a bunch of words. Okay, what problem are you having?
I just said my problem was just like getting from one word to the next word, like how to make it like stop.
Okay. So, I mean, the key to, when you're given a string that contains a bunch of words and you've got to turn each one to Pig Latin, you need to iterate through you need to take the string and use it to build a scanner. And then you can just get one token after another out of the scanner. As you get the word out, each time through the loop, you get a new word out of the scanner, you'll convert it to Pig Latin using the method you wrote above. And then append it to a string that you're building as a result. So it's an accumulation loop that consumes a scanner and builds a string. That's the best high-level advice I can give you. But to go along with that, I don't think I've ever had a student that came to my office with a question about a loop, and my response to them was, "Oh, you need to make your loop more complicated." It's astounding how complicated some of the loops get that I see. And what I usually end up doing to the student is getting rid of most of the code. And I think what happens is you start with a simple loop, it doesn't quite work, and so you make it more complicated to cover some case you didn't think of, and eventually it's completely out of control. The examples we've been doing of accumulation loops that we did last time, I think we've done 6 examples. The code you're writing for loops in PS3 aren't any more complicated than those. You really can do them the way I described in lecture last time, by starting with a enumeration loop and adding 3 lines of code. One to initialize the accumulation variable, one to update it, one to return it. And you just believe me, you can do it that way. And that's the simplest way to do it. So if you keep the faith and sort of stick to the straight and narrow path, you'll have less trouble, I believe. Any other questions? Yes?
So Zybook shows us quite a bit of 4 examples, but I haven't really come across that yet in our class. Is 4 something you use that often, or do you
Okay.
actually just go with a lot?
So I've had you reading the Zybook, and its treatment of loops talks about 4 loops pretty quickly. We're not always in exact sync with the Zybook. In terms of loops, Java has while loops, which we've seen. It has do while loops, which are slightly different. And it has for loops, which are different. And it has for each loops, which we'll eventually encounter. And we'll talk about all of them. Anything you can do with a while loop, anything you do with any of those loops, you can do with a while loop. Sometimes it's more convenient to use the other forms, but I prefer to stick just with while loops at the beginning, get used to the idea of repetition. And then I can say, this for loop is just like this kind of while loop. We'll eventually get there. Any other questions? Okay. Let's look at something different. So we talked about accumulation loops. Let's talk about searching loops. So as it says there, searching loop is what you use to find an element that satisfies a property. So you've got a range of integers, or you've got a string of characters, or you've got a scanner full of tokens, or eventually we'll see arrays and lists and maps and sets and whatever. A searching loop finds some element in some collection that satisfies some property. For example, maybe we write a method to find a prime number from a list of numbers. Or we want to find the least popular song on a playlist. Oh, that's actually not right. We want to find an unpopular song on a playlist. All right. I have a. I'm going to change this right now because this isn't right. Searching loops, you're not looking for the least popular song. You're just looking for, let's say, what is a Beatles. You're not looking for the one best song. You're just looking for a song that has some property. So you got a playlist and you want to find a song by the Beatles or a song by Green Day or whatever. Which team is in first place? Which team has a winning record? Okay, so we'll look later at optimization loops where you're trying to answer questions like what is the best or what is the worst. Here we're just asking, find me something that satisfies this property. Right. Glad I got that straightened out. So let's see how that works. So suppose we want to write a searching loop that we're given essentially a list of integers, a range of integers to consider. So just like we've been saying, we're told where to start and how many integers to consider. And we want to find some integer that satisfies some property. Like we want to find an even integer in that range, which would be kind of easy. We want to find a prime number in that range. We want to find a perfect square in that range. Whatever. So just like with accumulation loops, you start with an enumeration loop. So I've written up there the standard form for an enumeration loop. And to turn this into an accumulation loop, we added code up here to declare the accumulation variable, code in the loop to update the accumulation variable, and code below the loop to return the accumulation variable. To make a searching loop, you just change it in two places. So let's go back to this version. This version is just, each time through the loop, it's looking at a different value of I. So what we do is, each time we get a different value of I, we ask, does I satisfy some property? So this thing in angle brackets obviously isn't Java code. It's just meant to, there'll be some expression in here that'll tell us whether I satisfies a property. And what do we do if I satisfies a property? What if I is prime, or I is even, or I is perfect square? That's what we're looking for. What does the program do at that point? Yeah? It not only exits a loop, it exits the method, it returns. So if I is what we're looking for, then we return I. That ends the loop right then, it ends the method, and whoever called the method gets their answer. Okay? So when you return, no matter where the return appears, that ends the method. Okay? Now, when would we get to this right here? This last statement says return a value that indicates failure. Yeah?
When it goes through all of I from start plus n.
Okay, so if it's looked at every I and none of them satisfy the property, that's the only circumstance under which the loop will terminate. In that case, we've got to do something to tell whoever called us that we didn't find something with that property. And one way to do that is to return some special value that indicates failure. So maybe if you're looking for a prime number and you don't find one, you return -1 or 0. It just has to be in the specification of the method. You have to agree what you're supposed to return. Yeah? Is there a reason I'm not using I++? That's just one more thing to explain that I'd rather not do right now. Okay? This always happens. Students want to use this I equals I plus 1. You can just write I++, semicolon, and it does the same thing. So there, I've explained it. But there's some subtleties with that. There are ways to use I++ other than as a statement that get confusing. Because all you're doing is replacing I equals I plus 1 with I++. It's easy. Or plus I. We had a discussion on Piazza last night about this. Okay, so there's searching loop on a range of integers. Now, here, suppose you want to search for a character in a string that has some property. So again, we start with an enumeration loop. That's the enumeration loop for strings. Right? We iterate through the string. Each time through the loop, we grab a character out, and when we're and we do something with the character. Now, what's it going to take to turn this into a searching loop? Remember that to turn the original, the integer loop into a searching loop, we had to add the if inside the loop, and then we had to add a return at the end. So what do you think we do to this one to turn it into a searching loop? Yeah, same thing. We add an if that says, okay, if C is what we're looking for, we return it. And if the loop terminates, then we return some value that indicates that we didn't find the thing we were looking for. So it's the same way with accumulation loops. There are three different kinds of loops we're looking at, or three base enumeration loops for integers, for strings, for scanners. Once you can write the enumeration loop, turning it to a searching loop is the same exercise. You add the same type of code in the same places in the loop. I mean, that loop right there looks very different from that loop right there, but they're essentially, to my eye, they're about the same thing. They're going through a collection of things and searching for something in the collection that satisfies a property. Right? There's our prototypical enumeration loop for scanners. You know, while the scanner has an X token, you get the token out and do something with it. What's it take to turn that into a searching loop? Yeah? Yeah, same thing again. If that token is what you're looking for, you return it. Otherwise, if you fail, you return a value that indicates failure. So next week, when you're writing searching loops on PS4, remember this. You don't have to, if you're writing a searching loop, it's going to look like one of these models I gave you. You just got to take the enumeration loop and add a couple of pieces of code. Doesn't have to be complicated. Okay, let's put this into practice, though. So here I have a method. It's called findInt with large cosine. Okay, it says returns an integer between 1 and n that has a cosine greater than 0.99. If there is no such integer, it returns 0. And I have already written the enumeration loop there. So it starts at I. Well, let's see if I did it right. Returns an integer between 1 and n. So I already see a mistake I made in the enumeration loop here. This is a little different from what we usually see because there's not a start and an n as a parameter. There's just n. So I'm not actually enumerating all the integers. So how do I fix this? What's the problem? What if I put in this blank right here, suppose I just put a system.out.println I. What would this loop print? If I gave it 10 as a parameter, n is 10, what would it print out? It would print out 1 and then 2. What would be the last thing it printed? 9. I want it to print 10. So I should have made this less than or equal. Okay. So I got the loop that can enumerate the integers that I need. Each time through the loop, I'm going to get a different integer. And I want to return an integer. If I find one with a cosine greater than 0.99, I want to return it. So how do I do that? What's the pattern? All right, I need a conditional here. And if I was what I was looking for, I want to return it. How do I know if I is what I was looking for?
Cosine is greater than 0.99.
Yeah, I just do with math.cosine is greater than 0.99. Then I return I. Oh, okay. I make mistakes too. What mistake did I make here? Yeah? Yeah, I'm taking the cosine of n, which would be the same time. I need to be taking the cosine of I. Okay? So if we found what we're looking for, return it. Now, this is supposed to be returning a number that indicates failure, and it just says up here, return 0 if there's no such integer, so I've already got it there. If it said return -1, I'd put -1 there. But there, once I got the, let's start with the code for an enumeration loop, which I had to modify slightly from what we normally do. Turning it into a searching loop wasn't too hard. You just got to think, if I found what I'm looking for, return it. And if the loop ends, then I return the flag that says the thing failed. So it doesn't have to be hard. Any questions about that? Okay, here's a string. So maybe the string S coming in, maybe it's A, B, C, D, or maybe it's A, B, 4, 7, 6. What this is supposed to do is look for a digit in the string. Look for a character that is a digit. And if it finds it, return the digit. And if it doesn't find it, return underscore for whatever reason. So we're just trying to find some digit. Doesn't matter which one, if there's multiple digits. Just find some digit if it's in there and return it. So I start with my typical enumeration loop for strings. It just marches through the string. And I guess I could add a little bit more code here. I could say, I put the code in there to get the character out. What do I need to add to this? Right? An if. So if we find what we're looking for, return it. And how do we know if we found what we're looking for?
C equals whatever you're looking for.
Well, if C is a digit. So you might be wondering, how do you test if it's a digit? Well, I just know that they're in the character class. There's a method called isDigit. Not called that. It's called isDigit. And what are we supposed to return if we don't find a digit? It said underscore, so I'll do an underscore. Done. So where do you have to think when you do this? I contend there was only really one place where I had to be at all creative to get this loop to work, given that I know the pattern that all searching loops fall into. Yeah, it's really just how do you do that? How do you tell if the thing is what you're looking for? If we find it, we're going to return C. Well, you know that, so we just got to get that right. It says in the spec what to return if you don't find it. So that's not much thinking either. So they really can be this easy. Any questions I can answer about that one? I'm going to skip over this. These are accumulation loops. Let's come down to here. If a scanner contains a token of the desired length, returns it. So we're given a scanner that has some tokens in it, and this is a desired length like 5. So if we find a token of length 5 in the scanner, we return it. Otherwise, we return the empty string. Okay? And I've written there the the basics of a enumeration loop for scanners. What do we have to add? Yeah, just a conditional. If we found what we're looking for, what do we return? Yeah, we return the token. If we don't find what we're looking for, return the empty string. That's good. So we just got to be able to tell right here. How do we know if the token is one we're looking for? What code do I put there? Someone want to commit to it and say it out loud? If token, now we can't say if token equals desired length. Token dot length is the same as desired length. So maybe at this point you're understanding why I started out the semester by talking about expressions. Because essentially this is, well, that's an expression right there. So being able to come up with the right expressions to control a loop or a conditional is an important skill to have. And I have an easier time than you because I've done it a lot more, but also I know I have a lot of the methods that you can apply to strings memorized, but it's not too hard to find out, to guess that, okay, to get the length of a string, maybe it's size, maybe it's length. You know there's got to be some method to do it. It's not that hard to find. Okay? Now, when you get your assignment, PS4, the method bodies will be empty except for a stub return statement. What's the first thing you ought to do? What's the way to get started on these methods? What did we talk about last time? Yeah. Say again. Yeah, paste in an enumeration loop. Get that looking right. And then add the pieces. Or you could also just copy an existing searching loop and customize it. Well, let's try that. That's another accumulation loop. That's no good. Okay. Returns an integer token from numbers that has at least n factors. Returns 0 if there's no such token. Well, okay. That's not going to work. We're going to have to write this accumulation loop because I want to use that in the other method. All right. So let's look at this one. How do I know, besides the fact that it says in the comment this is an accumulation loop, how would you classify this as an accumulation loop as opposed to a searching loop if you're just reading the first line of the comment? What gives it away? Well, first of all, why do you know it's not a searching loop?
Because you're returning one.
Yeah, you're not returning an element, you're not returning an integer between 1 and n or anything. You're returning a count of something. So it's an accumulation loop. You're combining, in some sense, everything from 1 to n into an overall answer. So to make an accumulation loop, we've got to start with an accumulation variable. So I'm going to call it count, because we're counting how many, well, let's do it. Let's do num factors. So there's our accumulation variable. It starts at 0. When the loop is done, what do we return? In an accumulation loop, typically, what do you return at the end of the method? The accumulation variable, right? So we'll return that. And then in here, we need to update the accumulation variable each time. And there's a slight twist here because what do we want to do to num factors each time through? How do we change num factors as we encounter each I in this loop? We want to add 1 to it if what? Trying to count the factors of n. So if I is a factor of n, we want to add 1 to num factors. How do you tell if I is a factor of n? say n is 9 and you're looking at 3. How do you tell 3 is a factor of 9? What was that? Okay, I'm going to have to get closer. Say it again.
There's a remainder of 0.
Remainder of 0. You do the division and look at the remainder. So this is a different kind of accumulation loop. I think we saw one last time in that there's a conditional involved as well. So it sort of looks like a searching loop in a sense because there's an if, but it's really an accumulation loop. Here, I'll do that. So that adds 1 to num factors. And we only want to add 1 to num factors if I is a factor. And we know that if we take n and mod it with I, we get 0. So that's probably the hardest part of that method right there, is knowing that that's how you figure that out. So if I evenly divides n, we increment num factors, and when we're all done, we return it. So that'll just count how many i's actually divide n evenly. Okay. And it looks different from our usual accumulation loop because there's a conditional, but sometimes you gotta be flexible. All right, now down here. I want to find a number that has at least n factors. So I'm given a string of numbers. In this case, this example, it contains these 6 numbers. And then I've got a target, 4. So what I'm saying is I want to find a number in here that has at least 4 factors. Now 1 doesn't have 4. How many factors does 1 have? Just 1. What about 2? It's divisible by 1 and 2. 3 is divisible by 1 and 3. That's still just 2 factors. 4 is divisible by 1, 2, and 4. That's just 3. 6 is divisible by 1, 2, 3, 6. So it has 4 factors, and we'd return 6. So there it is. I'll give you a few minutes to figure it out. This is a searching loop, so you're going to add some code here, and you're going to add some, possibly, you don't even have to change that. It says return 0 if there's no such token. And actually, let me make this easier for you. When we pull the tokens out of this thing, we ought to pull them out as ints, because we need ints. So given that as your starting point, design the if statement that goes right here. If something, okay, talk to people around you. Tell me what I put here inside those parentheses and what I put here inside the braces. Okay, let me see what you came up with. Let's start right here in the braces. What do we return if the condition is true? Yeah? Okay, so we return number. If you find number, we're testing number to see if it's what we're looking for. If it is, we return it. That's pretty automatic. Now there's a test here. Now we want to return the number if it has at least n factors. Yeah?
You do a method call of number of factors that we just did.
Right. Here's the key thing. We just finished writing this method. Let's use it. Sometimes you don't write a method just because someone tells you to. You write it because you need it to do something else. So in this case, it's really handy to have a method called number of factors. I don't know of one in the library, so we just use it. So we say if number of factors of number. Okay, so that'll tell us the number of factors that number has. How do we finish the test? Right. So if the number of factors of the number is n, or well, return number. That's not quite right, though. What mistake did I make? Yeah. Greater than or equal. I said at least n factors, so, or the comment did. That's what I'd want to do. Some days I make mistakes on purpose, just to show you what's going on. Today I'm not having to make them on purpose. I'm making them organically, just for whatever reason. Okay? So there are a couple of lessons here. Again, the code that you had to add the enumeration loop was pretty simple. Just a test to see if what you're looking for is, if you found what you're looking for, and if you find it, you return it. That's straightforward. The one leap was, you may have been thinking as you're sitting there working on it, oh, there must be a method in the integer class that counts factors. There isn't, but we just wrote one that does exactly what we need, so we use it. Now, sometimes you'll be programming, and it goes the other way. You say, you know, what I really need is a method that counts number of factors. If only a method that counts factors existed, it would be really easy to do this. And then, if there is no such method, what do you have to do? You have to make it. So you go somewhere else in this file and write this method. Okay? I call that the programming by wishful thinking. If you find yourself wishing for a method, if this other method existed, this first method would be simple to implement. Wish for what you need. If it already exists in the library, use it. If it doesn't, create it. We're not quite there yet, but it's always good to look ahead. All right, now, we also get a lot of questions about this yellow line that underlines this variable right here. It says resource leak nums is never closed. So if that really bugs you, what you have to do is, before every return statement, you have to close the scanner. Semicolon. All right, and that takes care of the yellow underline. But that is really not the best way to close a scanner. So I would prefer if you just put up with the yellow underline. That's a warning, not an error. It's a potential resource leak, but actually in this case it's nothing. And in a few weeks I'll show you the right way to close scanners and other things. So for now, just don't worry about that warning about resource leak. We'll deal with that in the future. Okay? So that's searching loops. So before we turn to the next kind of loop I want to talk about, are there any questions about searching loops I could answer? Yeah?
So think about the examples you had on the screen at the beginning of class, like find a Beatles song. If I wanted a search loop that didn't break after just finding the first result, would I use a combination of accumulation loop and a search loop to tally all the results? And
Okay.
return them?
All right, so good question. Suppose that you had a list of songs and you're supposed to find all the Beatles songs, not just some of them. Not just one, but all of them. So it would be sort of like this accumulation loop right here, where the code would be, if this song is a Beatles song, you would have to do something like add the Beatles song to some list you're building. And then when you're all done, you return the list. But we haven't talked about lists yet, so we will. But it'd be more like an accumulation loop than a searching loop. Except it'd be an accumulation loop with a conditional in the middle, which sort of looks like a searching loop. So your intuition is right. Any other questions? All right. Yes, I got a question.
So, for the second one down where it returns the number that, like, which is the criteria for number of factors.
Okay, where are we? Down here?
Yes, that one. So, will that return every number that meets that criteria?
Okay. So the question is, suppose we had also, besides a 6 in here, suppose we had like 100, which certainly has more than four, it has more than 4 factors. The question is, does this return the 6 and the 100 or just the 6? So what do you think? Okay, it returns just the 6. Why doesn't it return just the 100? Yeah? Right, as soon as it encounters the 6, we return, and that ends the loop, ends the method, nothing else happens. If there was a way to go backwards through a scanner, then we would encounter the 100 first, and it would get returned first, and the 6 wouldn't be seen. So whatever one we find first ends the whole show. Any other questions? Yeah.
Aren't you supposed to define number of factors in this class, or can you carry it over from a previous, or in a new
Okay.
method?
So he asked, suppose number of factors wasn't in this class. Suppose it was in a different class. Could you use it? Okay? And the answer is, yeah, you could use it. Just like scanners in a different class, and we're able to use it. You would import it up here. So, yeah. Yeah.
So like, for some reason you would like call a variable number, like in that last method we were talking about, instead of return number. It would, if you were to have that list including that 100, would it return 6 or 100?
I didn't hear part of your question. So, suppose. Go ahead.
Instead of returning number, you just have some variable, like integer number is equal to something, and then you set return number and you return it somewhere else.
Yeah, so let's let me change this slightly. Suppose we don't know, we haven't talked about list yet, but we have talked about strings. So suppose I wanted to get, we'll call this all in factors. Not the best name, but the idea is it's going to return every number from that string that has 4 n or more factors. So the way you do that is, now you conceive of it as an accumulation loop. So we would say, we'll have a result here that starts out as the empty string. And when what we're going to return is a string containing all the numbers. So we'll advertise this returns a string. When we're all done, we're going to return the result, whatever it is. And then we just got to change what happens right here. When we find a number that's good enough, what do we do with it? If we're not going to return it, what are we going to do with it?
Result equals result plus.
We're going to combine result and put in a blank space maybe, and then add number to it. So we sort of converted that searching loop into one that it doesn't return just the first one it finds. It builds a string that contains every one that it finds. So now it's an accumulation loop. And what we would get back when we call it on this string right here is a string that contains 6 and a space and 100. And we'll eventually learn better ways to return a collection of things than putting them into a string. But right now, that's the most convenient thing I have to work with. Any other questions? All right, let's take a couple of minutes and we'll look at optimization loops. Wrong place. Okay. Third, we've talked about accumulation loops, searching loops, now optimization loops. So an optimization loop finds superlatives. So it finds the smallest or the largest, or the heaviest, the lightest, the nicest, the meanest. There's always a superlative word in the specification. So for example, what is the highest grade in a list of grades, or the least popular song on the playlist, or which team is in first place. And a common problem you encounter when you do that, which you also saw with searching loops, is suppose you are given no elements. Suppose there isn't a superlative because there's nothing in the collection. What do you return? We always have to sort of deal with that. So let me show you how it works. Here again, we'll start with the enumeration loop for a range of integers. And suppose we're supposed to find, maybe we're supposed to find the integer in that range with the most factors, or the least factors, or the number with the largest cosine, or the smallest cosine, or whatever. That would be our starting point, and we've got to turn it to an optimization loop. And we're going to add code in 3 places. We're going to add some code up here. We're going to add some code in here. And we're going to add some code down here at the bottom. And let me just show you what code you have to add. So here I'm assuming that there's at least one element. If you're willing to assume that, this is what you do. We create a variable called best so far, or maybe we can think of a better one than usually, like, best song or largest number or whatever. But I'm going to call it best so far. And we initialize it to the first integer in the range. Now, if it turns out that that's the only integer in the range because the value of n up here is 1, that's going to be our answer. If there's only one thing, it's got to be the answer. Then we modify the enumeration loop slightly by starting it with, adding 1 to the starting point. Normally we don't do that. Then inside the loop, if we find an I that's better than the best one we've seen so far, then the new best so far is I. So why does that make sense? Why are we checking to see if the current I, remember we're counting through a bunch of I's, if we find one that's better than best so far, why does it make sense to assign I to best so far? Yeah?
Because then you can compare further values to that best so far.
Okay. So you think then you can compare future values to that best so far. Essentially, think of best so far as the current champion. And if something beats the champion, it becomes a champion. So when the loop ends, the value of best so far will be the answer. And that's what we return. And you're always faced with the question, what's the initial value of best so far? If you can assume there's at least one element, the simplest thing to initialize best so far to is the first element. Now, because initially that is the best so far. Why do I do a +1 right here? Yeah?
You don't need to compare best so far to itself.
Right. There's no need to look at the first element because it's already stored in best so far. We know it's not going to be better than itself. So it'd be kind of a waste of time. Now what if I didn't put the +1 there? Would that cause a problem? Would we get the wrong answer? No. It's just slightly less efficient. A little cleaner not to consider it. Now, what do you do if, well, first let me see if there are any questions I could answer about this. So the 3 parts in yellow there are, you declare a variable to contain the best so far, and the type of that variable is going to be the same as the type of the method returns. At the bottom, you return best so far. And then your job is, as the loop goes on, you keep updating best so far every time you find a new champion. So those are the three pieces you stick into the enumeration loop. So any questions I could answer about that? We'll see examples in a few minutes. But. Now, what if you are not allowed to assume? What if there's a possibility there will be no elements? Like the string is going to be empty, or the scanner could be empty, or the integer interval could be empty. what do we do then? We can't initialize best so far to the first element if there is no first element.
Do we just put a conditional in if there's nothing there and you just,
Okay, we could put a conditional in. So the first thing you could do is say, if there are no elements, do something. And what something should we do if there are no elements to look at?
add elements?
You know, eventually we'll learn how to throw exceptions. So one thing we might do is throw an exception. The specification has to tell us what to do if there are no elements. So I'm going to show. I just got rid of all the yellows. All I did. Now I'm going to change this into a version of the loop that doesn't make the assumption that there's at least one element. This is one way to do it. So what you can do is initialize best so far to some impossibly bad integer. So by impossibly bad, I mean as bad as an integer could possibly be. And ideally, it needs to be a value that normally you wouldn't return. So what would be a thing you can initialize best so far to? Let's say, we have to make this concrete. Suppose you have a list of ages, and you're supposed to return the smallest age in the list. Okay? What would be an impossibly bad age?
-1.
-1. Right? No one has an age of -1, and furthermore, -1 is worse, i.e., what are we supposed to find? I said it backwards. Let's look for the largest age. Okay? So -1 is an impossible answer, but furthermore, it's worse than any possible other answer. So we start things out with an age of -1. If the list is empty, if there are no ages, we're going to return -1 as the answer. And that will signal that the list was empty. No one had an age, so I'm returning -1. If there's any age whatsoever in the list, though, even if it's 0, it's going to be a champion when it's compared to -1. Now, what if we were trying to find the lowest age? Where could we, what could we use as an impossibly large value of best so far? 200, because nobody ever lives to 200, but what if the ages are of redwood trees? Positive infinity, yeah. Which there isn't one in Java, but there is a largest integer, which is like 2 billion. And then someone's going to tell me there's a stand of trees in central Utah that's 2 billion years old. I don't think so. But. Okay, so I don't make a too big a deal about this, but the difference between when you're allowed to assume there's one element, you sort of prime the pump with the first element. When you're not allowed to make that assumption, one way to do it, you don't have to do it this way, is to start best so far out as being an impossibly bad answer. In the two properties you need, it needs to be an impossible answer that you wouldn't get normally, and it needs to be worse than any possible correct answer. So a negative age or an infinite age. And then notice also that if we're doing it this way, we do have to look at the first element, assuming there is one. Okay. Here's an enumeration loop on strings. What are we going to have to do to turn it into an optimization loop? By now, you're experts at this. What do we paste into the blank spots there? Same stuff we pasted in before. There's those 3 yellow chunks. And that's assuming there's at least one character. So we initialize best so far to be the first character and then start with I equals 1. Okay? What if we don't want to make that assumption? How would we change this? Yeah? Yeah, we have an impossibly bad character, and we start with I equals 0. And scanner, same deal. You paste in the 3 same chunks of code if you're assuming there's at least one token. Otherwise, you do that. Now let's just look at this, though. This is kind of unusual in that we call scan.next here, and we call scan.next here. So this removes the first element that we're assuming is there, and this gets the rest of them. All right, so enough of this in the abstract. Let's look at it. Let's look at the examples. So here's my class, optimization loops. Let's write some optimization loops. Now, before we wrote a method that found a cosine, it looked for a number with a cosine greater than 0.99. This case, what I want to find is a number, the number with the largest cosine. So returns the integer between 1 and n that has the largest cosine. And we require n to be at least 1. Now, what's important about that assumption? Yeah?
The cosine of 0 is 1.
Well, the cosine of 0 is 1, but we're not considering 0. We're just looking at 1 through n. But what case does this leave us in? Are we in the case where we can assume there's at least one element in the collection, or can the collection possibly be empty? Right, we can assume there's at least one, which is the number 1. N is at least 1, so at worst, the numbers we look at is the sequence 1. It might be 1, 2, it might be 1 to 100. It's at least going to be 1 to 1. So we can assume there is at least one element. So under that assumption, what do we need to change about what do we need to add to our loop here? No, we have to add some code here. We have to add some code here. And we have to return the right thing down here. So what code goes at the beginning to make it into an optimization loop? Yeah?
Probably a number that's like largest number so far.
Okay. So we have to declare our best so far variable. So what type does that variable have to be? How do you know what type it is? Well, we're returning an int, so it better be an int. So we're going to say int. And you can literally call it best so far unless you can think of a better name. We could call it number with largest cosine so far. I'm just going to say best so far because I don't want to type that. And what should we initialize it to? We're assuming the sequence isn't empty. There's at least one number in the sequence. So we want to use the first number in the sequence, which is always going to be 1. Because this thing looks at the numbers between 1 and n. So we'll start that at 1. And usually in an enumeration loop, you initialize I to be the first element in the sequence. In this case, what should we initialize it to? 2. Yeah, because we've already dealt with the first element's already stored in best so far. There's no need to look at the first element again. So we go one further. Okay, when we're all done, what do we return as our answer? Best so far. And then, in here, we need to put code that updates best so far if we find a new champion. So if we find a new champion, the new value of best so far will be I. Well, how do we know if I is the new champion?
I is greater than best so far.
Well, is it that? If I is greater than best so far? That's not quite right, because that's not what we're trying to optimize. If the cosine of I is greater than the cosine of best so far, we found a new champion. So we say math.cosine of I is greater than math.cosine of best so far. So if that's true, we found a new champion and we update best so far. Okay? So this is a little more complicated than a searching loop or an accumulation loop. Sort of has elements of both. And it might be worth it to try to track through what's happening. So let's do that. That's not what I wanted to do. Let me put a breakpoint right here. And let's go see, up here we're calling find int of 100. That's not going to work. Let's do find largest cosine of 10. So we're going to be looking through the numbers 1 to 10 to find the largest cosine. And then we're going to run it in debug mode. Hello. Okay. So that's where it's gotten to. And rather than use that magnifying glass thing, which makes it hard for me to control this, I'll just tell you when the numbers change over there. Right now it says n is equal to 10. So we're going to initialize best so far to 1 and set I to 2. So over there on the right it now says n is 10, best so far is 1, I is 2. While I is less than or equal to n, I is still small enough, so we continue. It's now going to compare math.cosine of I to math.cosine of best so far. Now, what has a larger cosine? 1 or 2? Right? I is 2, best so far is 1. So 1 has a larger cosine than 2? So if that's the case, which I believe it is, 2 should become the new champion, right? So let's see. No, I guess it wasn't. Okay, I is 3. So now I is 3, best so far is still 1. Is the cosine of 3 greater than the cosine of 1? Well, let's just let it find out for us. Nope. Okay, now we got I is 4. Is the cosine of I bigger than the cosine of 1? It's the cosine of 4 bigger than the cosine of 1. I don't know. Not the best example because I don't know what the answer ever is. Let's see if we can ever find one that's bigger. Apparently 6 has a larger cosine than, so currently best so far is 1, I is 6. This is in radians, not degrees, by the way. So we found a new champion, 6. And we keep going around. Now we consider 7. That didn't work. 8 doesn't work. 9 doesn't work. 10 didn't work. And we're about to return 6 because that was the best one we found. So that's how the loop works. Just search through all the possibilities. Whenever it finds something better than the best it's found so far, that's the new value. When we're all done, we just return it. Any questions I could answer about that? Let's see. There it is. And just to emphasize, suppose you just started out with the first, which is what the numeration loop does. The loop would just run one extra useless time, comparing the cosine of 1 to the cosine of 1. So it's really not a big deal. Okay, let's find the largest character in S, which is required to be non-empty. So I tend to make that the assumption you can make, that the sequence is non-empty, so you don't have to worry about inventing an impossibly large, an impossible value for best so far. So there is our prototypical enumeration loop. How do we turn it into something that finds the largest character in S? Now, before we do that, we ought to agree what we mean by the largest character in S. And what I'm after is, I'm going to call B a larger character than A because B comes after A in alphabetical order. And then we're going to generalize that and just say whichever character has a larger Unicode value is bigger than a character than the other character. And we find that just by comparing them with greater than. So we'll use the greater than to compare characters to find out which is bigger. Okay? So what do we need to add? First of all, where do we need to add it? Where do we have to put in pieces of code? Yep.
In the brackets of the while loop.
Okay, we've got to add code right here to update best so far. What else do we have to add? We've got to declare our best so far variable there. And down here we've got to remember to return it. Well, this time I can think of a better name for best so far. What could we call it? Yeah. Largest char. I could say largest char so far, but all right, what am I doing? And what should we initialize it to? We want to initialize it to the first thing in the sequence, which is what in this case? All right, char at 0 is the first. And then what can we make that to make it just a little? Yeah. So we won't bother looking at character 0 in this loop because we've already accounted for it. When we're all done, we're just going to return largest char. So this part's always easy. Now we just had to figure out, let me add one bit of code before we do that. Okay, so that's the character. How do we update it? What do we put there? How do we know that we found a character that's bigger than any we've seen before? Okay.
Char index is greater than largest char.
Right. So if C is bigger, we have a new champion. And what you put in the braces is always an update of largest char. And that does it. So let's see what largest char is. So we got A, B, C, 1, 2, 3. Well, let me change this slightly. Let's try that out in the debugger. So we launch it here. Okay, so you saw the string that I gave it, which we can also look at right here. It is CBA, then capital A, B, C, and then 3, 2, 1. So we are initializing largest char to that first letter in that string. So I'll step over that, and largest char starts out as C. Then we set index to 1. We enter the loop. We pull a character out, which is B. And is B bigger than C? Nope. So that doesn't get updated. Next character is our A. What's bigger? C. So our current champion remains the current champion. Then we've got capital A. Is capital A bigger than little a? Nope. Next is capital B. That's not bigger. It's just the order. The capital letters come before the lowercase letters in Unicode is all you're seeing here. That doesn't get updated. I may have made another mistake in this test case. A 3. Is the character 3 larger than the character lowercase c? I don't know. I hope so. It's not, rats. So this thing never gets updated because the first thing we chose was the champion, and we end up returning C. If I had constructed the string slightly differently, which I think I will do, just
in Unicode, don't the numbers come before all the letters?
Yeah, I forgot that in the heat of the moment. So where are we? There you are. Okay, so I changed it to ABC at first, so we can at least see an update. So we come in here. C is B, largest char is A, and the B happens to be greater than A, so it'll update largest char. So now largest char is B, our character coming in is C, that's larger than the B, so we're going to update. So now largest char is C, and then it's going to stay the same. The rest of the string is like before, and eventually return C. So you get the feel for how that works, I hope. Any questions I could answer before I look at another example? Okay. Find longest token. So got a scanner with a bunch of tokens in it. I just want to know the longest token. And we're going to assume that the scanner is not empty. So this should become familiar by now. We got to declare something there. We've got to update something there, and we got to return the right thing here. So what goes up here? Right, string longest token, and how can we initialize it since we know there's going to be at least one token? It's just s.next. We just take the first thing out of the scanner, and the reason we can do it without checking to see if there's a token there is because we're allowed to assume there's at least one. Right, when we're all done, we're just going to return longest token. And in here we have to crown a new champion if there is a new champion. So what is our, we're going to do that. When will we update longest token to be the new champion? Well, we already did the s.next. So there I've taken the token out of the scanner, so I've done that for you. If token's length is greater than longest token dot length. We do that. Now, if you're having trouble visualizing what happens when this program runs, when this method runs, I encourage you to do what I've been doing. Just set a breakpoint and single step through and watch what happens as it runs. That can really cement how this is working if you watch it unfold in time. Because it's easy for me to look at this and say, yeah, I see what that does, although I do make mistakes all the time with loops. I get the gist of it pretty quickly without thinking too hard. But at first, it helps to visualize it if you sort of run it in your head. Now I'm going to do one last thing. Returns the integer between 1 and n with the most factors. If n is not positive, returns 0. So now we're not allowed to assume that there's at least one number to look at. So how is this going to be different from what we did before? What's our impossible number? What's that?
-1.
We could use -1, but because that's certainly not going to be an answer. The answer is going to be between 1 and n. So -1 is, it's impossible answer and it's smaller than any of the other answers. But there's one that's slightly better. 0. Now why is 0 better than -1 in this case? Because that's what we're going to return in the case that we don't find any integers at all, and so we won't have to do any extra work. We just return this number here. So this is going to be what do we call it? Best so far. I gave it 2 seconds. I couldn't think of anything better. So initialize that to 0. We'll return best so far, and we have to have our if here. And this code almost writes itself. What assignment goes inside the if?
New champion.
We just update best so far with the new champion. How do we know if I is the new champion? If I has more factors than best so far. Well, how do we tell whether I has, how many factors I has? If only there were a method, I wish there were a method that would tell me how many factors I has. We just wrote one. It's in the searching loops class. And it's called number of factors. So if the number of factors of I is greater than number of factors, where'd it go, of best so far, then we update best so far. Now, I said before something that wasn't quite accurate. I said if we want to use a method from another class, we have to import it. But it's not making us import it here. This is sort of a fine point. It's not a very interesting point. Who knows why we don't have to import searching loops? Yeah? Because it's in the same package. You automatically get access to all the classes that are in package CS1410, which are if we look at Project Explorer over here, no, not that one. Well, anyway, there's a handful of classes in CS 1410 that we have access to them all automatically. So what we did was we don't have to copy the code over, paste it into this class. It's in the same project of Eclipse, in the same package, so we just call it. Okay? All right. So finish up PS3, and I'll get PS4 out.